Okay, we're going to have a look at the more about differentiation in the notes. So if you have the official CA notes, we've got second derivative tests for turning points. We talked about that last week, and max and min problems. Second derivative is just when you do it again, differentiate again. So if you look at the example 1, so differentiate it once, you get 3 minus 3x squared. Differentiate it twice, so it's minus 6x. Just make sure you write it properly. It's d2y over dx squared. That's very important. Now, the turning points. We already talked about the turning points. It says here, if the second derivative is under 0, the gradient is decreasing, blah, 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 it's a maximum. And if the second derivative is bigger than 0, it's a minimum. So let's have a look at the second example here. Find the turning points of this curve. So y equals 3x minus x squared. So first of all, we're going to do is we're going to find dy by dx. So we've got to differentiate this. So if you differentiate 3x, you get 3. If you differentiate this, you get minus 3x squared. Put it equal to 0. Bring that over, divide by 3. And remember when you're doing the square root, it's plus or minus square root. Now you're looking for points, so don't forget to find the y coordinate. So when x is 1, put it in to get the y coordinate. So 3 times 1 minus 1 cubed gives you 2. And do the same when x is minus 1. Put it in to get the y coordinate. 3 times minus 1 minus 1 cubed. So you've got the x and y coordinates for both. Now you've got to find the second derivative to determine their nature. So this is your dy by dx. Sometimes it's quite nice actually to write dy by dx out clearer so you can find it when you're looking back through your work, because you have to differentiate this again. So if you differentiate that again, 3 disappears, becomes minus 6x. Then what you do, when x is 1, put in 1, and you'll see it's under 0, so it's a maximum. And then over here, your second derivative is minus 6x. Put your x in, and it works to be positive, bigger than 0, so it's a minimum. Now, that principle is used a lot in practical questions, so I think we've got 2 questions here to run through. This is what gets a little bit tricky, but we'll try our best. So example 3, a rectangular sheet of metal, which is 1 metre across, has squares cut from each corner, and each square is x by x, and it's folded up to give an open box. So if you imagine that's 1, each of these wee squares are x, and this is the whole length is 1. So whenever you fold up your box, the base of your box is 1 minus 2x. And this is going to be the base of your box here, which is 1 minus 2x. Now, the question then is wanting us, let's check what it says here. Okay, find the maximum possible volume. Now, do you see that word there, maximum? That's your key, that it's this topic. Maximum or minimum, you treat like curves. So you differentiate it, set it equal to 0, basically find the max min point, which is your turning point, and then check if it's max min by doing the second derivative. It's always that system. So maximum point of the volume. So the volume is the length of the box times the breadth of the box times the height. So you times out these brackets and tidy it up. I've now got an expression for the volume. To find the maximum volume, you differentiate this to 1 minus 8x plus 12x squared. You put it equal to 0. So just put in this expression equal to 0. You can factorise it or use the formula. Now I have got 2 answers. X is a sixth and x is a half. So what I'm going to do now, I'm going to find the second derivative to see if I can find which one is the maximum. If you differentiate this again, so down here, differentiating this, 1 disappears, that becomes minus 8, that becomes 24x. You have 2 choices. X is a sixth, so put that into the second derivative, so it's minus 8 plus 24 times a sixth. That works out to be under 0, so it's maximum. And if you put in x equals a half to your second derivative, you get minus 8 plus 24 a half. Bigger than 0, so it's minimum. And then you have to work out the volume. So you can use any of your expressions for volume. I used the first one. Volume is 1 minus 2 times your x. So I'm choosing my x to be a sixth because I want the maximum one. So 2 times a sixth, square it, because you have 2 of those, times a sixth gives you the volume. So maximum volume is 2 over 27 at x equals a sixth. So just before we go on to the second example, I'm just going to write out a few wee key points. So you have got turning curve, curve, and then you have got practical problems. Now, for the curve, you would go dy by dx equals 0 for the turning point. For practical problems, dy by dx, but might be dv by dx, or whatever your variables are, but it's the same principle for max, min. Okay. Over here on the turning point, you find x, then sub in to find y. Over here, you find your variable, whatever it is. It could be x, it could be whatever. Then sub in to answer question. So what do I mean by that? If we look back over the question you've just done, the practical problem 1, instead of dy by dx, we had dv by dx equals 0. So we solved it. We got our x's. Then you sub your x in to your v, into your volume, to answer the question, because the question wanted what is the maximum volume. So that's your first stage. Then you always, on a curve, you differentiate again and sub in x. And if the second derivative is bigger than 0, it's a minimum. And if your second derivative is under 0, it's a maximum. It's exactly the same over here. You do your second derivative and sub in your variable, whatever it is. We'll just call it x. And if your second derivative is bigger than 0, it's minimum. And if it is less than 0, it's maximum. So it's the same problem. Okay. Over here, you will see the key word will be turning point or stationary point. And over on this side, the key word will be max or min. Now, we're going to have a look at example 4. This is the last one in our notes. Yeah, so example 4, very common question, this one. A farmer wants to make a pen for a goat using the side of a barn on one side of the pen. He wants to have an area of 50. So that's my first piece of information. If you can see here, the area is x times y and has to equal 50. Now, he wants to use as little fencing as possible. So you want to have the minimum fencing. So the length has to be minimum. So 2y add x is the length. Now, if you notice this time, I have got 2 variables over here. Compare that to the previous example. You just had x's. Now I've got x and y. But on this question, you were given more information. You were given this top line. So what you do here is you rearrange this to get y equals. Take that y and put it in here. So you've got 50 over x add x. You've got 100x plus x. So now you have got your expression in terms of x's. In order to differentiate that, you write that as 100, bring your x up, so x minus 1 add x. Now you just go through the process as normal. Differentiate L with respect to x, minus 100x minus 2, add 1. Put that equal to 0. Now to solve this, I made it a wee bit neater. Minus 100 over x squared, add 1 equals 0. Bring this over to our side, so it's 1 minus 100 over x squared. Bring your x squared up. X squared is 100, so x is plus or minus 10. Now obviously you can't have minus 10 as an answer because x is a length, so you choose x to be 10, as you can't have a negative length. So once you've worked out x equals 10, you can work out your y if you want, but the question wanted you to find the length. So you can just put it straight into the length. Length is up here. 100 over 10 plus 10 gives you 20. Don't forget to do your second derivative. So here's my first derivative. Differentiate it again. 200x minus 3. That can be written as 200 over x3. Sub in your x is 10. You can see it's bigger than 0 and it's a maximum.